The remainder of our topics for this week are going to be momentum and collisions. Now, these rams both have a lot of momentum and they're about to collide. And we're going to talk a little bit about what happens during collisions, how momentum is conserved, and sometimes energy is conserved, and sometimes it's not. Linear momentum is the product of the velocity vector and an object's mass. So sometimes we represent momentum as a capital P. P, momentum, is a vector. Momentum is equal to our mass times the velocity vector. Okay, so whatever direction the velocity is in, that's the direction that the momentum is in. And momentum has units of kilograms meter over second. Okay, kilogram meter over second. If you forget, you can remember it because you know that momentum is a mass times a velocity. Mass is kilogram, of velocity is meters per second. So momentum must be a kilogram meter per second. We don't have a special unit to represent momentum. Okay, it's just kilogram meter over second. Momentum comes out of a consequence of Newton's second law. So let's come over here. We've got Newton's second law, the net force is equal to the mass times the acceleration. Remember that the acceleration is the rate of change of speed. So you can rewrite the acceleration as the change in speed over the change in time. So if we bring that m inside this little delta sign, our change in, that says that our force is equal to the change in mass times velocity over the change in time. So that's change, that mass times velocity, we also said is the same thing as momentum. So Newton's second law, you can also repurpose it to say that the net force is equal to the change in momentum over a change in time. So the net force on an object is equal to the change in momentum over the change in time. That directly comes out of Newton's second law. So we call this, if we rearrange this to solve for momentum, we have that the net force times the change in time is equal to the momentum. That's just taking the previous equation that we saw and solving it for momentum. Momentum, or the change in momentum, is equal to the net force supplied times the change in time. And we give this special name here, our net force times our change in time, we call that the impulse. The impulse is equal to our change in momentum. So no matter what, whenever you have a collision, you have that quantity for momentum, okay? But you can change this right-hand side or this left-hand side over here, okay? So if the change of momentum is constant in a collision, okay, some objects hitting each other, you can reduce this net force by lengthening the amount of time over which this collision happens. You can increase this net force by decreasing the length of time over which this collision happens. No matter what, when you multiply the net force times the change in time, it has to stay constant for the change in momentum. But you can make one of these quantities on the left-hand side larger and the other smaller, or vice versa, and still keep the change in momentum the same. Okay, so let's think about this in terms of our crash test dummy here. Our change in momentum, we've got our mass times our final velocity minus our initial velocity. Final velocity is going to be 0. Our initial velocity was how fast we were moving before that crash. Okay, the change in momentum is going to remain the same whether or not we have an airbag. When that airbag deploys, you can lengthen the duration of your body coming forward and slamming in to that steering wheel, okay? You can lengthen that amount of time, but the change in momentum has to be the same. So if you lengthen that time, then you can reduce the force on your body during that collision experience, okay? And so that is kind of an example of impulse and change in momentum in action. This idea is exactly why football players wear padding when they play their games. That padding, you know, the change in momentum has to be the same when they slam into each other, okay? But you can lengthen the duration of that collision by adding that extra padding, and then that reduces the net force that's applied on your body or even applied on your brain. A collision is a short duration interaction between two objects. Okay, so here we've got a soccer ball. Your foot is hitting the soccer ball. At the minute the foot touches the soccer ball, contact between the objects begin. Okay, there's going to be some time period where your foot is in contact with the ball. Okay, so halfway through that, or maybe not necessarily halfway through that, but around halfway through that collision of your foot and the ball, you reach maximum compression of that soccer ball. You're going to change the shape of the soccer ball while your foot is impacting it. And then at the end, your foot is done impacting the ball. Your foot stops being in contact with the foot, well, if you're not American, a football, but if you're American, a soccer ball. Okay, so during the collision, it takes time to compress this object, and it takes time for that object to re-expand. The duration of your collision depends on the material. Okay, so that's your delta T in the impulse equation. And that force is the force that's being applied by the contact between those two objects. So F delta T is equal to your change in momentum. When you're kicking the soccer ball, the amount by which the ball is compressed is a measure of the magnitude of the force that your foot exerts on the ball. The force is only applied while the ball is in contact with your foot. You have to be in contact in order to apply that force. This is a contact force, not a force over a distance like gravitational forces are. Okay, so the impulse force is a large force exerted during a very short time interval. So here is a plot of what this impulse force might look like during a collision. So here, contact between the football or the soccer ball and the foot begins, okay? And then that we're increasing that contact force as we increase the compression of that soccer ball on the foot when we're halfway through the collision. Eventually, we'll reach a point of maximum compression of the soccer ball, and at that point is where we have the greatest amount of force that's being applied on the soccer ball, okay? And then halfway through towards the end of our collision, the contact force is diminishing and eventually contact ends. And so this is a plot of what the force applied looks like during a collision. We've got our time period over which this collision is happening, and this is a plot of what that force looks like during the collision. So as we already talked about, if the duration of this collision could be increased, the force of the impact will be decreased. Again, here's another thing where we're thinking about the area underneath the curve. The impulse is equal to the area underneath a force versus time graph. So our total impulse is going to be this area underneath this curve right here. That total impulse has to equal our change in momentum. Okay, so if we could somehow figure out what this area is, we could increase the duration, decrease this force here, but still maintain the same area underneath the curve, and in which case, then our F times delta T, that whole area underneath the curve, would be the same, and that equals your change in momentum, which always remains constant. Okay, so we're going to apply this idea to this little question right here. Okay, we have two 1 kilogram stationary cue balls, and they're struck by a cue stick. Okay, I'm thinking about pool, billiards. This ball right here is struck by a cue stick, and the duration of that impact is 2 milliseconds. That's what this little m here means. Milli is 10 to the minus 3. 2 times 10 to the minus 3 seconds is the duration of that impact. This is our force applied. So the impulse is equal to the area underneath this force versus time graph, okay? And then over here, we have our second ball, our second billiard ball. It's being struck by a cue, by a pool stick, okay? The duration of that collision is 20 milliseconds, but the force applied is only 10 newtons, okay? So in this first one, the collision happened over 2 milliseconds. The force applied was 100 newtons for that whole time. And then over here, we've got the collision taking place over 20 milliseconds, and that whole time, the force applied was 10 newtons. So which ball has the greater final speed? Is it ball 1, ball 2, or do both balls have the same speed? So remember that the impulse is equal to the force applied over the time period, okay? That's also the area underneath this force versus time graph. That has to equal your change in momentum. Our change in momentum is going to be the mass of the object, which doesn't change, times your final velocity minus your initial velocity. So with that in mind, which one of these two cue balls had the greater final speed? Was it our first ball here, our second ball, or are they both the same speed? Now we're going to use this idea of impulse in order for you to answer the discussion for this week, okay? So we have a golf ball with some mass, and it's being struck by a golf club. That's what this picture is showing us right here. The force on the ball varies from 0, right at the moment when the contact is made, up to some maximum value when our ball is most maximally deformed, and then back to 0 when the ball leaves the club again. Just like our foot on the football, we have here our golf club on the our golf club on the golf ball. So over some time period t, you see that the force increases and then it decreases again during the impact. Okay. Assuming that the ball leaves the club with some velocity, find the magnitude of the impulse during the collision. So the magnitude of the impulse during the collision is also the same thing as the change in momentum. You know the mass and you know the speed at which the ball is leaving the club, you can find the momentum, because we're going to assume it starts from rest. Okay, you can find the impulse by finding the change in momentum. And then you're going to estimate the duration of this collision and the average force acting on the ball during this collision. So how are we going to solve that? Okay, so we need to find our average force. Our average force is going to equal to our change in momentum over our change in time, because remember that our change in momentum is also equal to the impulse. That's our average force times the time during which this collision is happening. So if we solve that for the average force, well, you can get at the average force on the ball by knowing the change in momentum from part A divided by the time during which this collision happens. So I guess the magic is, we already know delta P from part A. How do you find the change in time here? Well, here's something you could think about. How do we find the change in time? Well, let's see. We know that a speed is equal to a change in position over a change in time. So if we solve that for delta t is equal to our change in position over a speed. So if you can figure out what this average speed is during the collision, which is usually about half, or you can take it to be about half of the maximum speed at which the ball leaves the club, you can think of that as the average speed, okay? I've given you a lot of hints in order to solve this problem. I'm going to leave it up to you to figure out, what is this change in position? What is that distance over which this collision is occurring, okay? Which is essentially the distance over which that golf club is in contact with the golf ball. What is that distance? So think about it. Think about, maybe you want to think about the size of your golf ball, what happens when the club is in contact with the ball, when does the ball begin its trajectory, okay, relative to where it's sitting on the golf tee. So I'll let you think about that in order to get an estimate at this distance here over which this collision is occurring. So once you find that, you've got the average speed of your golf ball when it leaves the club, okay? You're gonna find out what is this position or this distance over which this impact between the club and the ball is occurring. Once you get that, then you can take this quantity and you can stick it in here for this equation for your average force that the club is exerting on the ball, okay? So the magic here is figuring out what is this time over which this collision occurs, which you can figure out by thinking about the distance over which this collision is happening. And so you're gonna have to apply your physics brain, do some estimation, think about what reasonable quantities you might need in order to solve this problem.